Now we come to one of the other important equations in this chapter. Ohm's law, V equals IR, is really one of the most important of the laws that we talk about. But another very important law relates power to current and voltage. P equals IV is a very, very important equation when we want to calculate how much energy a particular electrical device will dissipate in a given amount of time. Now in a circuit, electrical energy goes by how much charge we move across a particular potential difference. Remember, potential difference, voltage, is energy per charge. So if we take the amount of charge, we multiply it by voltage, we're going to get how much energy. Okay? Where does that energy go? Well, some of that energy oftentimes is simply converted into heat. Sometimes the energy is converted into light. Sometimes it's used to create work. But in any case, anytime we move current across this potential difference, energy will be converted from an electrical form to another form of energy. So again, here is our circuit. We have a battery right here. It's going to pass through, the current is going to pass through a resistor. It's connected to ground. That just means that the negative side is going to be hooked up to 0 volts like the rest of the earth. And if we think about this, on this side we have the battery. The battery is going to convert chemical energy into electrical energy. As the current flows to this side, that electrical energy now can be converted into other forms of energy. Through the resistor, there's going to be a potential drop. Again, the amount of charge that passes through the resistor times the potential difference will tell me how much of that energy is taken out of the system in the form of electrical energy. And for a resistor, it simply converts that into heat. Okay? So, energy in to the system, a battery converts chemical energy into electrical energy. Energy out, the resistor converts electrical energy into heat. Now again, we're not so interested in calculating a set amount of energy. We're interested in how much energy is being consumed in a given amount of time. We're interested in power. So again, charge times potential difference gives us the energy. If we want power, we have to take that as a rate per unit time. So again, we're going to go back to our early definition for power. Power was energy per unit time, the rate that energy was used per time. We can go back to our earlier discussion and say, well, in terms of the infinitesimal energy that flows through any given section, that is going to be equal to the charge that flows through times the potential difference that it experiences. Okay, so Q times V. We'll take this Q out in front, and now we have dQ dt. That is the rate of charge flow. Well, that's simply current. So again, deriving power from what we previously know about the flow of charge and the amount of energy per coulomb gives us a very simple expression for power, where power equals current times voltage. Okay, so P equals IV, our power equation. That's also a very important equation for this chapter. Almost as important as V equals IR, P equals IV. Let's take V. We'll replace V with IR. I times IR becomes I squared R. Here's another version of power. This shows us that the power dissipated, the power used by any electrical device, is equal to the current that flows through it times the resistance of that device. We can also write it as power, replace the I is equal to V over R. V over R times V becomes V squared over R. The power used by any electrical device is equal to V squared divided by R. V is the potential drop, the potential difference across the device or appliance. Okay? That depends on what the device is doing within the circuit itself, divided by its resistance. Okay? So when we look at this, we can use P equals IV to calculate the power as long as we know current and we know voltage. or as long as we can find current or voltage based on the resistance. So let's calculate the power of an appliance that's drawing 8 amps with a potential of 120 volts. Once again, we can use any of these forms right here. We're given current and voltage, so we'll just leave it as P equals IV. Power equals current times voltage, 8 amps, 120 volts. Remember what the units for power are. Units for power are watts. So this particular device drawing at 8 amps, normal house voltage, we're going to use about 960 watts, roughly almost a kilowatt. Okay? Here's another case where we're calculating. Here we're going to use this a little bit differently. We're going to calculate the current through an appliance with a power consumption of 380 watts. Again, it's hooked to house current, so it's 120 volts. P equals IV, but now we're going to solve for I. I equals power divided by voltage. 380 watts divided by 120 volts. That tells me to use this much power at 120 volts, we're drawing 3.2 amps. Now, think about the power system, the grid. What delivers electricity to our homes? What is amazing is how much they boost the voltage to send it a long distance. All right, let's try to understand this a little bit. Energy is generated at the power station. Chemical energy, maybe nuclear energy, maybe light energy from solar panels, maybe wind energy, some type of either a very large station or a small device is generating this power initially. Now, to dump it on the grid, they go from a lower voltage to a higher voltage. They've got to send it along these blue lines. Now, these blue lines are basically representing cables, probably made out of aluminum. Some of the older ones might be made out of copper, but I'm pretty sure they've pretty much gone to all aluminum. They have a finite amount of resistance, okay? So even though they can be fairly thick transmission cables, they're not zero resistive, okay? They're not superconductors. They will always convert some of the energy through them, V equals IR, but P equals IV. They're always going to produce some of the, convert some of the electricity through them into heat. They're going to lose energy, okay? So we boost it to a high voltage and then we drop it back down when it's delivered to, let's say, an industrial customer or maybe even your home, because at these voltages, 138 kilovolts, 230 volts, even up to a megavolt, we wouldn't want that type of high voltage in our home. It would be not only dangerous, it would be highly destructive. So we boost the voltage high, drop it back down when it gets to our house. Why do we do this? Well, if you think about that equation, power equals current squared times resistance. It's the current that causes us to lose a lot of the energy. So we can send the energy at a higher voltage, get the same power to our customers, but lose less energy from the resistance of the lines. Because again, P equals I squared R. It's the I squared. You double the current, you lose 4 times as much energy over the grid. And these are just a map of some of the primary transmission lines, the electrical transmission lines that are used to carry power from different parts of the state. And the color corresponds to different voltages that they're sent. But again, the lowest voltages in kilovolts is about 115 kilovolts. The highest on this map is half a megavolt, but they are starting to put together megavolt DC transmission lines because, again, by making this voltage higher, the power lost just from heating up the lines, sending electricity through them, is much, much lower. If you're not convinced, let's do a little calculation. Let's say that we have to deliver 10 megawatts. 1 times 10 to the 7 watts of power to our customers. Okay? To do that, we can send it at a low voltage, high current, or high voltage, low current. Okay? In this particular case, I'm going to say the power lines that we use have a certain amount of resistance. I'm trying to think of how I set the resistance here. I think I set the resistance to say that the power lines have 2 ohms of resistance. Okay, can't remember exactly what I set it at, but I think that's pretty close to this. Okay, so in any case, maybe 20 ohms of resistance. Let's go with that. If I set it at 100 volts, which is pretty close to what our house voltage is, I would have to send it at 100,000 amps. But 100,000 amps, do the calculation. P equals I squared R. Again, we're going to set R to roughly 20 ohms. You would have to send an absolutely ridiculous amount of energy down the lines just to get 10 megawatts at the end. Okay? You would have to send 2 gigawatts of power. You would lose 200,000, I'm sorry, you'd lose 20,000% of your energy just on the transmission of the lines compared to the actual power that you delivered. Double the voltage, the current is cut in half, you cut your losses by a quarter. Okay? And again, you can see in this red, we're losing more energy than we're actually delivering. It's not until we're down to about here where we're actually losing less energy heating up the lines than we're delivering to our customers. Here, we're sending it at 50,000 volts. The current drops to 200 amps. This is about the lowest that high voltage lines will send voltage, about 100,000 volts, about 100 kilovolts. And even there, we'd have about a 20% loss, okay? It's not until we get our long transmission lines saying that their total resistance is about 20 ohms, out to 500,000 volts, that we can drop the current to only 20 ohms, and here we're losing only about 0.8% of the total energy over the lines. So again, it makes a lot of sense. Delivering the same amount of power requires us to boost the voltage up over long distances. Yes, it's expensive to put these high voltage lines on these tall towers, and it can look quite ugly. But honestly, and that's the only way we can deliver energy efficiently. So by the time it gets to wherever we're sending it, we'll get to like a small town. There'll be a substation there. It'll drop the voltage to a few tens of kilovolts. It rides on the top of the pole, probably to the outermost customers at about 5,000 volts. Those little transformers that are on the telephone pole, they'll then drop it to about 120 volts. That goes into your home. And here, in fact, is one of those power transmission cables. Again, you can see it's been cut into a few different layers. It's made out of aluminum. It can be rather thick. Again, this is a typical 100-mile long high voltage power line. It's going to carry the voltage at almost a megavolt, 765 kilovolts, and delivering 1 gigawatt of power to the customers. It'll lose 0.5% to at most 1% of its energy during transmission. Again, if all the loss is due to resistance, how much current does this line carry? Let's say if it's only losing 1% loss, 1 gigawatt, 1% of 1 gigawatt is 10 megawatts. Thus the power delivered again is 1 gigawatt. We can look at the current. This big transmission line would carry about 1,300 amps. Again, very thick. But again, to deliver this much power, all right, we want to keep our losses as low as possible. Calculating the resistance of the line, let's say we lose 10 megawatts of power delivering this. We can say power is equal to current squared divided by, power squared times resistance. We want to find the resistance. Resistance is equal to power divided by I squared. And This particular line has a resistance of 5.9 ohms. So our first example, 20 ohms, wasn't all that far off. Again, electrical units of energy and power. Energy in SI units is always joules. Power is watts. Again, I is amps, R is ohms, and V is volts. Keep everything in SI units, and then it's easy to convert from one unit to the other. A kilowatt hour is not power. A kilowatt hour is energy. It's the energy used if you have a